Hello, dear students. Uh, we have started our unit number 4, linear transformation of mathematics paper 1, linear algebra. Now, this is our lecture number 6, and in this video, we are going to see existence of linear transformation and examples based on existence of linear transformation. So, first of all, see existence of linear transformation. It is theorem. If the set containing vectors u1, u2, etc. un is a basis for vector space phi and w1, w2, etc. wn are arbitrary vectors in W, not necessarily distinct, then there exists a linear transformation T from phi to W such that T of ui is wi or I equal to 1, 2, etc. and means T of u1 is w1, T of u2 is w2, etc. T of un is wn means if you have a basis for vector space phi and if you take images of this basis vector, then this will form or this will be a linear transformation from vector space phi to vector space W. So our assumption is that the set B containing vectors u1, u2, etc. un is a basis for phi. So let u belongs to phi be arbitrary vector in phi. Now, since B is the basis, U can be written as linear combination of these basis vectors. So, you must have scalars k1, k2, etc. kn such that U equal to k1 u1 plus k2 u2 plus etc. kn un. And the scalars k1, k2, etc. kn form an n-dimensional vector, and this vector is called coordinate vector relative to the basis B. So we have a coordinate vector. So this suggests that we can define a map T from V to W as T of U is K1 W1 plus K2 W2 plus etc. Kn Wn. So existence of these scalars suggests that we can define a map T from V to W such that T of U is K1 W1 plus K2 W2 plus etc. Kn Wn. Now we have to show that this T is a linear transformation. So let two vectors U and V are arbitrary vectors in V, and therefore we have a scalars k1, k2, etc. kn and c1, c2, etc. cn such that U can be written as k1 u1 plus k2 u2 plus etc. kn un, as well as V can be written as linear combination of vectors c1 u1 plus c2 u2 plus etc. cn un, and therefore T operating on U plus V is whatever U is here, K1 U1 plus etc. Kn Un, and V is C1 U1 plus etc. Cn Un. Now collect the coefficients of Ui's together. So you will get T as it is in bracket. You will get K1 plus C1 outside of the bracket U1 plus etc. Kn plus Cn outside Un. Now since T is a linear transformation, so you can take this scalar outside. So you will get K1 C1 times T of U1, but T of U1 is W1, then K2 plus C2, then T of U2 is W2, etc. So you will get K1 W1 plus etc. Kn Wn and plus C1 W1 plus etc. Cn Wn, and therefore we must have. Now here we have not used the T of U1 is W1, just we have used the definition of T as T operating on U is some scalar into W1 plus some scalar into W2 etc. some scalar into Wn, and you will get T of u plus v is T of u plus T of v, and thus we have T of u plus v is Tu plus Tv for every uv belongs to v. Now second case, let alpha be any scalar, so you will get T alpha u is alpha times whatever this k1 u1 plus k2 u2 is your u. So use the definition of T here. So alpha k1 is scalar, so alpha k1 w1 plus alpha k2 w2 plus etc. alpha kn wn. Now take alpha outside, k1 w1 plus etc. kn wn, and this is nothing but your T of u, and thus we have T of alpha u is alpha times T of u for every u belongs to v and for any scalar alpha, and thus by 1 and 2 we conclude that T is a linear transformation. And now for each I, this ui can be written as 0 times u1 plus 0 times u2 plus etc. 1 times ui plus etc. 0 un, and therefore we must have T of ui is 0, 0 times w1 plus etc. 1 time wi plus etc. 0 time wn, that is T of ui is wi for each I running from 1 to n, and thus we have a linear transformation T from v to w and T of ui is wi for I running from 1 to n, and this completes the group of theorem. Let's see examples how this theorem works here. So let B is the set containing vector u1, u2. Here u1 is order pair 1 1 and u2 is order pair 2 0. Be a basis for R2, and T from R2 to R3 be a linear transformation such that T of u1 is minus 1, 3, 4. T of u2 is 0, 2, minus 5. Find formula for T and use it to compute T of minus 2, 3 or T of anything. But here our main target is to find formula for T, means T of xy is equal to what? So we want general formula. Here we have given that the images of basis vector. So let xy belongs to R2 be arbitrary vector. So let me erase this. So let order pair xy is the member of two-dimensional vector space R2. Now as B containing the vectors u1, u2 is a basis for R2, this xy can be written as linear combination of basis vector. So we must have scalars k1, k2 such that xy can be written as k1 u1 plus k2 u2. Now put u1 here, or same calculation we will see afterward. Now apply T on both sides. So T of xy is T of k1 u1 plus k2 u2. Now since T is a linear transformation, you can take scalar outside. So k1 T of u1 plus k2 T of u2. Now we have given that T of u1 is minus 1, 3, 4. So put here, and T of u2 is 0, 2, minus 5. So multiply k1 inside, multiply k2 inside, and make the sum in R3. So you will get T of xy is, this is minus k1 plus 0 times k2. So first component is minus k1, middle component 3k1 plus 2k2, and the third component 4k1 minus 5k2. Here bracket is missing. So this is T of xy. Now we want k1, k2 in terms of x and y. Now we have xy equal to k1 u1 plus k2 u2. So this equation you can put u1 is order pair 1 1 and u2 is order pair 2 0 and simplify this. So we have xy equal to, so u1 is order pair 1 1, u2 is order pair to 0. So multiply k1 inside, simplify this. So you will get first component is k1 plus 2k2 and the second component is k1. So equate these order pairs. So you will get k1 plus 2k2 is x and this k1 is y. So already we have k1 is y. So put k1 equal to y in the in this equation and find out k2. So you will get k2 is x minus y divided by 2 and thus we have k1 is y and k2 is x minus y divided by 2. So put these values in t of xy. So we have already equation 1. So here instead of k1 we have here minus y, then middle component just replace k1 and k2 by k1 by y and k2 by x minus y divided by 2. Simplify this, you will get t of xy is first component minus y, second component x plus 2y and the third component is minus 5x plus 13y divided by 2 and this gives the formula for t. So t from R2 to R3. If you want, you can verify whether this t is a linear transformation. So definitely this will be a linear transformation. So we have a formula for t of xy. So to compute t of minus 2, 3, just put x equal to minus 2 here and y equal to 3. So you will get t of minus 2, 3 equal to minus 3, 4 and 49 by 2. So this is an easy example. So just let me revise this. This is important, this equation, because we have to use this equation twice. So to find the formula for t, so choose arbitrary vector from domain vector space. So here our domain vector space is R2. So we have chosen order pair xy belongs to R2. Now we have again given that basis for domain vector space and therefore this arbitrary vector can be written as linear combination of basis vector. Once you write this equation, so you have to solve this equation in two ways. So first apply t on both sides, simplify. So you will get t of xy in terms of k1, k2. Secondly, replace u1 and u2 and solve this equation for k1, k2 in terms of xy and just put k1 and k2 in this equation. So you will get formula for t of xy. So this type of examples are very important. So for practice purpose, I have given you some examples. So you can solve these examples at your own. So these are exercises. So you can refer this previous example and solve this example. So find formula for t of xy z. Let us stop here.